Now that is our first concentration inequality. Many of you may have seen it before. Now of course there might be multiple concentration, or rather multiple random variables with the same mean but then different variances, right. So you might have two different set of points, maybe a bunch of points here, and then my experiment is picking one of these points at random. Well, the mean is going to be somewhere here, right. So that would be the average value, right, the expected value of the experiment. Now if I instead change these set of points, right, here also the mean is going to be the same, right. So the expected value is still going to be the same for both these random variables. The experiment is among these 6 points. In each of these cases, pick one point at random. Let's say that's the uniformly at random. Let's say that's the experiment, right. In both the cases, the E of x, right. So if this random variable is x1, this random variable is x2, E of x1 equals E of x2. But in one case, the data points are far apart, which means that the variance is larger. In the other case, the variance is smaller, right. So somehow if we have this extra information about the variance, earlier we only had information about the mean. Now if I have some more information about the random process that's generating these points, I still don't know the exact distribution, but I know earlier I knew only mean, now I know mean and variance. Can I come up with a, perhaps in some cases at least, a better bound, right. And the answer is yes, you can do that, and that leads us to the second concentration inequality, which is called as the Chebyshev's inequality. This is also something that some of you may have seen earlier. If you have seen it earlier, try to recollect what this is. So this says that for any random variable x with well, there are some technical conditions, we won't delve too much into it. So the mean has to be finite and the variance has to be finite. So you have some mean, some finite number E of x, and some variance sigma squared. The inequality states that for any k greater than 0, the probability that, I'll write this and then we'll talk about this. This is one way of stating this inequality. It says that, well, I'm giving you the information about the variance and the expected value, and I'm asking, how much does the random variable deviate from its mean, right. So in an absolute sense, it can either go to the right side of the mean or the left side of the mean. But then what I'm asking is, if my mean is somewhere here, E of x, and now I am asking, what is the chance that my data concentrates, or the result of the experiment concentrates closer to the mean. In other words, I ask the question, what is the chance that if I do the experiment, I will find an outcome that is away from the mean, right. So by away, what do I mean by away? Away is this region. And how do I quantify that region? I am saying the absolute away is this region, and how am I quantifying that region is by asking the question, what the absolute difference between x, the outcome of the experiment, and its mean, right. So which means that the experiment might lead to an outcome here, then this would be the absolute difference, right. So an experiment might lead to an outcome here, then this distance would be the absolute difference. So I'm asking, what is the chance that if I do an experiment, I will get an outcome whose absolute difference from the mean is more than k times the standard deviation, right. So if you remember the Gaussian curve, for example, right, so you will have something like this, the bell curve, which is the PDF of the Gaussian. So the mean is 0, that's the standard Gaussian, and then you know, your standard deviation, one standard deviation is going to be somewhere here, which means that, you know, most of your times if you do an experiment, your points are going to be within this one standard deviation. But what this is saying is that for some choice of k, I am asking the question, what is the chance that the experiment's outcome deviates from its mean by k times the standard deviation? And Chebyshev's inequality says that, you know, this value, this probability is bounded at most by 1 over k squared. For example, what is the chance that it deviates 5 times, more than 5 times from the, you know, from 5 times the standard deviation, if the standard deviation is you know, so depending on the standard deviation, so this is going to be, so k times sigma is going to be 1 over k squared, right. So if it is 5, then this is going to be 1 by 25, right. So what is this is telling us is that the larger the deviation that we are asking for, right, so this becomes rarer and rarer, right. So if k becomes larger and larger, right, then that means that, you know, for k equals 1, we are looking at this region. For if this is the mean, for k equals 2, we are asking for this region, let's say, right. For k equals 10, we are asking for the experiment's outcome to be, you know, in this region. So now if the true mean is here, now we are asking, if I do an experiment, what is the chance that, you know, the outcome is here, right. So that's going to be lesser and lesser, right. So as the k becomes larger and larger, the chance that you are going to see rare events is going to go down, right. So and this is telling me that it goes down as 1 over k squared, right. So the larger the value of k, the smaller is 1 by k squared. And so the maximum probability, this is an upper bound, right. So even in the worst case, this is going to be 1 over k squared, right. So that's what your Chebyshev's inequality is. Again, I'm not going to prove any of these inequalities here, because that's something that you can easily do from a, you can, you know, you would have, or rather should have done it from a standard probability course. Here the idea is just to, you know, remind you or introduce you to these inequalities. Some of these inequalities will kind of use in some of our analysis later on in this course. So that's my Chebyshev inequality. Markov used only the expected value. Chebyshev uses both expected value and the standard deviation or the variance. Yeah.